In this video, we're going to be talking about 4.2 vector spaces. And before I get started, let me go ahead and talk about the 10 axioms of a vector space that are going to come up later. So you have 5 axioms that have to do with addition, and 5 axioms that have to do with multiplication. One through 5 here. Let me just give myself enough space for each of them. So the first one, and these are vectors u, v, and w that I'm going to talk about, and these are all elements of some proposed vector space V, and constants C and D are going to be real number scalars we're going to talk about. And I'll talk about what the zero vector is later when we get to that property. But number one is that when I add vectors u plus v that are in proposed vector space capital V, that the order of addition does not matter. So that's the commutative property of vector addition. Two is the associative property of vector addition. Okay. 3 is oh, I'm sorry. This is 3. This is 2. I forgot my closure property, which is the most important one. It's actually number 1. U plus V is in V, which is called closure under vector addition. Addition properties here. So closure means that, for example, when I add a real number to a real number, I get a real number. But just as for instance, when I add or subtract a number that is a irrational number to an irrational number, talking about subtraction here, right? That they may zero each other out and they may make a rational number, something like that. And so it's irrational numbers would not be closed under addition here, because I could add additive opposites here and get the zero for them, and zero is a rational number, not an irrational number. That would be an example of something that's not closed under addition. That we normally don't think of scalars like that as vectors. They're the first set of vectors that you learn these properties for. And so a lot of these things are like, yeah, that makes sense because I've been dealing with these properties with real numbers and other kinds of numbers for a long time. So, all right, here's kind of the big one where we have to define what the zero vector is. So capital V, the vector space, has a zero vector that's denoted the number zero with a line over it, such that for any and all U vectors that are in V, so I'm just using vector U in V, vector U plus the zero vector is equal to U, and that's called the additive identity. So the zero vector is the additive identity. And number 5 is going to be our additive inverse. So for all U that are in V, the opposite of U has to also be in V, such that U plus the opposite of U is equal to the zero vector. And again, that's the additive inverse. All right, let's move on to our multiplication properties here. Number 6 is that when I multiply a vector U that's in V by a scalar that's a real number, that has to be in V. So this is closure under scalar multiplication. It doesn't say anything about vector multiplication, just scalar multiplication. C, which is a constant, times the sum of U plus V, is the sum of the constant times U and the constant times V, which is the distributive property that I'm sure you know about. But there's another form of the distributive property that comes next, where we distribute a vector from the right over two constants. So C plus D times the vector U is going to be equal to CU plus DU. That's also distributive property. All right, let's get into our associative property that we know exists for multiplication. So C, and then times the quantity D times U is equal to CD times U. So that's our associative property. And last but not least is our scalar identity. So we need to be able to multiply by 1 and not change the vector. That's a scalar identity. And the reason I list all these out now at the beginning, so you can get them all written down, take a moment for that, is we're going to do some proofs in this section. And when we get to when we get to them, I'll tell you where they're at in the problem set, but we either need to find one of these things, any one of the things that doesn't work. If any one of them doesn't work, it's not a vector space. But to show that it is a vector space, we have to show that all 10 things do work. Now, your book does tell you a whole list of things that are vector spaces already, that are known vector spaces. Set of all continuous functions, the set of all polynomials of degree n or less, the set of all n by n matrices, the set of all n by m matrices, all these types of things, the set of real numbers, the set of R, all vectors in Rn, whatever n dimensional spaces that you're talking about, under standard operators. All these things are under standard addition and multiplication rules, and so on. So your teacher may just let you, in those cases, go ahead and just state that property. Ask your teacher about that. But you're going to get some problems where there's some non-standard operations defined for addition and multiplication, and you're going to have to test all of these rules and see if those non-standard addition and multiplication rules break any of these 10 axioms. Many times they do. That's the point of giving you the non-standard definitions of addition and multiplication, to see if you can figure out which of the rules get broken. Many times multiple rules get broken. You just need to find which one of the rules gets broken. So, okay, I have left those on the screen long enough for you, I think. I'm going to clear them and start to do some problems now. Reference your textbook if you need that list as we do the problems. So the first problem in 4.2 that I'm going to do is number 1, and it asks us to describe the additive identity for R4. Well, the additive identity, the zero vector for R4, is going to be a 4-tuple, all zeros there. Number 3 asks the same. This is for R4. This one is going to be for M 4, 3 is what we're looking at here. So the set of all 4x3 matrices. So 4 rows, 3 columns, all zeros. So what we're going to get for number 3. Let's move on to number 7, which asks us to describe the additive inverse for a generic vector that's in R3. So let's let the vector v, which is going to be equal to v1, v2, v3, be an element of R3. And then we need its additive opposite. So negative v1, v2, v3 is equal to the opposite of v1, the opposite of v2, and the opposite of v3. And that will also be in R3, so we're good. Number 9 asks us to find the additive opposite for a generic matrix 2, 3. So let A equal A, first row, first column, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column be an element of M2, 3. The opposite of A equals the opposite of A11, A12, A13, A21, A22, A23. By properties of matrices, we distribute that negative inside of everything. And that's it for that one. Moving on to number 13, this is where we start testing for vector spaces. So get your axioms ready. Number 13 asks us to determine whether the set together with its standard operations is a vector space, and if it is not, identify at least one of the 10 vector space axioms that fails. So M4,6 is the set of all 4x6 matrices. I already know from the fact that all n by m matrices form vector spaces under standard operations that it is. But let's go ahead and do what the teacher probably wants you to do here and show it generically. So let's test matrix A is going to be A11, A12, A13, A14, A15, and A16, A21, A22, A23, A24, A25, A26, A31, 32, 33, 34, 35, and 36, and 41, 42, 43, 44, 45, and 46. And then I'll need that also for matrix B here, which is B11. I'm just going to dot this to B16 and dot B61 to or 41 to B46. Just imagine that I wrote all that out there like I did with A. So my first one here is closure is A plus B is A11 plus B11, A12 plus B12, all the way out to A16 plus B16, A41 plus B41, A46 plus B46, and that is an element of M46. It's a 4x6 matrix. So I have passed the closure axiom for addition. 2 is A plus B equal to B plus A. We know it is under standard operations of vector addition. So yes. For matrices, the next one was the associative property is A plus, and I didn't define vector C, but is that equal to this? And we know it is because we know that that's an inherited property from all matrices. Is there a zero vector? There is. The zero vector is going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, and just all zeros here. And then we'll get A plus the zero matrix here is equal to A. Is good. 5 is there a negative A such that A plus negative A is equal to the zero matrix? Yes, there is. You can just change the sign on every single one of these, and that'll be a 4x6 matrix. Moving on to our multiplication axioms here. Just going to clear everything. Then I need to test number 5 is number 6 is C times A is in V, multiplying by constant doesn't make it not a 4x6 matrix, so that's true. And you can show that generically. 7C times U times A plus B. Well, we already know A plus B is a 4x6 matrix. Then we go back up here, so that's going to be in V. So, and that's going to be C A plus C B. We know that property, the distributive property, works for matrices. I'm not sure that we've seen this one in matrices yet, but yes, that works to multiply constants from the left like that and to distribute them across a matrix. So that'll be in there. We have order of multiplication of constants here. Does not matter for matrices. So under standard operations, and if I multiply 1 times matrix A, I get matrix A as well. So that doesn't have anything to do with the identity matrix that I can multiply by and not change it. That just has to do with the constant 1 that it exists, and that I can multiply by the scalar 1 and not change anything. So yes, M4,6 is a vector space. All right, that was one of the ones that I need to go through and kind of do all the steps for to be correct, though it is one of the ones that's just there in the book that you can say, oh, it's in my list of things I already knew. But let's go on to number 15, which we'll be able to disprove here, and it's the set of all third-degree polynomials. Now, the problem here, you may be thinking of something that's in the list that says P3, but that says the set of polynomials less than or equal to degree 3. So the set of all degree 3 polynomials. And the problem is that if I take, let's say x cubed plus negative x cubed, which are both degree 3 polynomials, I get 0, which is a constant, which is a 0 degree polynomial, which is not in my vector space. And so axiom 1 is violated. I'm sure there are others as well that are violated, like a constant multiple times it. If I did 0 times this, the 0 vector for this is not in that space either, because it's going to be the 0 vector for polynomials is going to be f of x equals 0, the constant 0. So it's not a third degree polynomial. You've got all kinds of violations of axioms here. Pick your favorite one and give a counterexample. I just gave one of the kinds of examples that you could give there. But I saw just off the top of my head that it violates axioms 1, 4, 6, 7, and 8. Maybe you find some other ones that it violates. So let's move on to number 17. We're in the form of ax such that a is not equal to 0. Is that a vector space? No, because we don't have a 0 vector there if a can't be equal to 0. So axiom 4 fails. That's the easy one to see. And then number 21, the set of all ordered pairs x, y in R2 such that is what that colon is. X is greater than or equal to 0, and y is any element of the real numbers. So we have a problem that if x has to be greater than or equal to 0, that we can't have a additive inverse that's going to equal the 0 vector as one of the things, but a real easy one here to see would be if I just multiplied by -1, which is kind of what I'm talking about with the additive inverse. That's not going to be in my vector space V necessarily. So let me show you that, like a -1, or let's just pick -2. So we're not picking on -1 times, and then 1, 1, let's say, is equal to -2, -2, which would not be in V, since -2 is not greater than or equal to 0, right? It's less than 0. So that is that one. All right, I'm going to clear the board here. Number 23 is another one that is a vector space, and I would have to show all 10 to prove it. So the set of all ordered pairs x, y, x, x, such that x is a real number. So we do have the 0 vector here because we have 0, 0, so that's good. That's one of the first things that I look for to see if we've kept ourselves from having a 0 vector. So if I have x plus y equals x plus y, which is going to be in V. X plus y equals x plus y, x plus y, y plus x, x equals y plus x, y plus x, which is equal to x plus y, x plus y. So we're good on number 2. Number 3 says if I have x plus y plus z, then that is going to be equal to x plus y plus z, y plus z is x plus y plus z, x plus y plus z. And if I would have x plus y plus z, and that's equal to x plus y, x plus y plus z is x plus y plus z, x plus y plus z. Number 4 says that we have a 0 vector. So x plus 0 equals x and 0 is in V. So we're good. Really, your 0 vector has to exist, but yeah, that's it. It's an existence axiom. So we need x plus negative x equals that 0 vector 0 and negative x is in V, so we have our additive inverse going on there. Let's clear this and look at the multiplication ones now. For 6, c times x is equal to cx, which is in V. 7 is we have c times u plus v, which is going to be x plus y. We get c times x plus y, is c times x plus y c times x plus y, and we want to see if that's the same as if I would take c times x plus c times y would be cx plus cy is equal to cx plus cy, and then I can factor c out here and factor the c out here, and we have the distributive property for number 7. Number 8 says c plus d of x should be equal to C plus D X. C plus D X is CX plus DX. CX plus DX. And I want to see if that's the same thing as CXX plus DX. X is CX plus DX. Yeah, that's right. They're all X's. Is CX plus DX. CX plus DX is the same thing. So we're good. Let's make a little bit more space to test 9 and 10. 9 says C times du. C times du C times dx dx, which is C dx C dx. Is that the same thing as CD times the vector xx? That's C dx C dx, so that's the same thing. And 10 says if I take 1 times x, that needs to equal xx, and it does. So therefore, V is a vector space. That was number 23 that was talking about V being the set of all x's such that x was an element of the real numbers. I have just a couple more here for us, so let's go on to number 41. And these will be under non-standard operations. And we're just going to do parts A and B of this problem. This will be it. This will be, just want to give you some exposure to testing for non-standard operations and looking for where you may have violated the axioms. So test if V is a vector space with the following non-standard conditions. So I'm going to have redefined addition for multiplication. It's rare that I exclude some constants from the vector space. Usually we just have all real numbers in the as our constant multipliers in the vector space. Usually that's not part of my non-standard conditions, but it could be. So watch out for that too. But if I don't give you non-standard conditions like this, then you would assume that standard conditions apply unless otherwise told. So This is our definition for addition for V. And this one is the standard definition. So that probably means that I'm not looking for an issue with the addition axioms, but I'm going to give you a non-standard definition for multiplication here, where I have only multiplied the first element in my vector and not my second element by my constant C, and that creates an issue for me. It's not a vector space because axiom 8 fails. So just for example, if I had 1 plus 2 times the vector 1, 1, that would normally be 3 times 1, 1, which by our definitions here would be 3, 1. But if I take 1 times 1, 1, plus 2 times 1, 1, that would be, by our definition of multiplication given here, 1, 1 plus 2, 1. And then using our standard definition of addition that's up here, that would give us 3, 2. And these things are not equal. So that's why axiom 8 fails. Let's look at part B of problem number 41. This time we're going to change the definition of addition. So x1, y1 plus x2, y2 is going to be equal to x1, 0. We're going to leave the standard definition of multiplication this time. So C, X, C, Y. So it's a subset of all vectors in R2 that meet this condition as the vector space. And again, you only need to find one axiom that doesn't work. So axiom 2 fails. I'm looking for a addition axiom probably that fails, and the order of addition matters here, which violates axiom 2, which says order doesn't matter. So just for example, if I had 1, 2 plus 2, 1, that's going to be equal to 1, 0. But if I switch that around and make that 2, 1 plus 1, 2, that would be equal to 2, 0. They're not equal to each other. So there's a bunch of other axioms that fail here. 4 and 5, also 8, even though 8's a multiplication axiom, it has to do with the distributive property of multiple scalars, and that would run into a problem here because you still have addition of those vectors at the end. So, all right, that is it for this video. We'll come back and talk about 4.3 next time, which are subspaces of vector spaces. So if we have known vector spaces, what is a subspace? We would call that capital W instead of capital V. How do we prove that something is a subspace? So if you want to think of, like, do you have a smaller group? We know the group of all 2x2 matrices is a vector space, but is there a smaller group of 2x2 matrices that with some restrictions, but it still meets all 10 axioms? That's kind of the example that you would think about. Can you condense it down some? How far down can you condense it before you start to lose the ability to do all 10 axioms? And there's some nice things that go on there, where we don't have to test all 10 axioms. We start off saying, well, really, you should test all 10 axioms on the subspace to prove that it's a subspace, but we really are only going to need to test the two closure axioms if we know that it's coming from a given vector space that already has all 10 axioms. We just need to prove that if we are in the subset of it and we add in the subset, we stay in that subset and don't go outside of it. And that if we are doing scalar multiplication in that subset, that we stay in that subset and we don't go outside of it. And that will be enough with the inheritance of all the other axioms from it being a vector space, that we can say that the subspace is also a vector space, or that the subset of the vector space is a vector space, so it's a subspace. So we'll talk about that next time in 4.3, and I'll see you for the next video.